This talk is going to be about radar and quantum mechanics, more radar than quantum mechanics. So I'm going to talk about radar and basically show how you can take something pretty grounded and, you know, pretty like a real thing and make it really abstract. But with reason, I think. And then little speculation at the end. I'm hoping I won't offend anybody except Nikki. I actually have
Well, I hope you won't offend
I was partially rearranging, you know, some slides that existed, and you know, I had to be very careful to pull out the things that said, you know, this is right. This is the guy that you want to blow up. And, you know, he's identified. Okay. And I guess I changed the title here a little bit. I've been pitching this idea a little bit to DARPA as an idea. So one of the things is the multidisciplinary aspect of this, and the way we do that is it comes from radar, but you know the computer science people would like it to be a state machine somehow. So we try and get it that way. And the interesting thing coming out of the biology community is, well, now they've got to the point, you know, they're digging down there for life, right? Trying to find out where's life. And they're down to DNA and RNA, and like looking at them, these large molecules as living organisms. They're just like, you know, they'll make a picture, here's DNA and RNA, and this DNA is kind of having relations with this other DNA. These are molecules. Right? So one of the interesting things is if you push that to atom from molecule, well, I think everything conceptually breaks down. This is an interesting thing. Yeah, so as I say, most of it is going to be about radar. I'm going to talk a little bit about how we deal with radar now, which is probably a little bit different than your grandfather's radar or Albert Einstein's radar. Then introduce generalized coordinates and path space in a certain way. I'm going to talk about generalized adaptive processing. The people that you know some physics will notice, well, I'll say as I go along. If you just blur your eyes and call this thing, which is W, and put instead the letter psi, you're going to see something. And then at the end, I'm going to get into the speculative stuff. By the way, my attitude is that if people are interrupting all the time, that's great. That's what I prefer. The first thing is, you know, nowadays, all of our radars have phased array antennas. And what that means is that essentially the radar has little tiny elements that have almost spherical patterns on them. And we have a lot of them lined up, either in a straight line or in an array. Okay? Now, the way these things work is they can detect angle. The way they detect angle is because if a plane wave comes along, right, each of these elements can detect the phase of the plane wave, and then in that way determine the direction. And I'll show you more specifically how you do that. But what I want to point out here is that the elements I can count through with an index and just call that, and I'm calling this just E for a shorthand, which is, you know, people tell me this is annoying because there's already an E that's taken, and then I use an I for something else. I have an index for the elements. I have an index. Okay, over here now there's a world of mathematics involved in all of this. But you know that if I have a signal of, and typically in real existing radars, we have a signal that has bandwidth that's limited, and a pulse that has a time that's ultimately limited. Right? So if the bandwidth and the time is limited, I can express what I have in that limited time by Fourier series. But because the bandwidth is limited, at some point there's a cutoff. So I only get so many terms of the series. This is the Shannon-Nyquist theorem. So it says that there's actually a certain number of terms, number of frequencies, equispaced, and the number of those is the bandwidth times the length of the pulse. And if I give the amplitude at each of those frequencies, I can reconstruct the entire signal of that thing. So what that means is a good representation of the signal that you're sending out and bringing back in is just in terms of the amplitudes, complex numbers at each of these frequencies. And you know, as engineers, we don't really mind about complex numbers. I mean, in the olden days, they used to talk about in phase and quadrature. This was in the day of analog stuff, right? And they would actually put a phase shifter on, so you would get the signal back. You'd sample it at one point, and then you'd sample it 90 degrees later and get numbers, right? This is a complex number. So from our point of view, we're just measuring the complex numbers. It's completely operational. But I have a set of these complex numbers that represent the amplitudes of a signal. And then typically we use a pulsed signal so that there's also an index for the time of the particular pulse. So you can picture this. I have a radar that's sending out a sequence of pulses. Each one of those contains a signal of a certain shape, right? And that's determined by this index. I send it out, I get something back again of the same kind, right? And that kind I can encapsulate down here at the bottom by saying, okay, there's a transfer function. Each sine wave, I have this wideband thing that consists of a number of frequencies. Each one of them is just like going on its own. And if the scattering is linear, it means it comes back with a phase shift and an amplitude change. And each one of those frequencies undergoes that. Well, that's it. You can put in a table these phase shifts and amplitude changes. And that's the transfer function. So that tells you what the world did to your signal. And notice, I'm not really bringing in geometrical things like the angles, distances, and all that initially. Think of this thing sitting here, sending out signal, bringing back signal, right? And in essence, in the computer, he waits a while. He writes down the signal he sent out, the signal he sent down, takes the ratio, and gets this object transfer function. That is, to the radar, the world, the universe. And I can, well, I'll show you what it can do with that. So what I want to tell you in this chart is just that we can encapsulate what the radar sends out, what it brings back, and really whatever it's learned about the world in terms of this function, which is a complex function, and it depends on indices, the wideband frequency, which is how we describe the shape of the pulse, the element, because I've got lots of radar elements, and the pulse time if I have pulses. And I'm just going to use some quantum mechanical notation and just say that's a vector. Okay? So I think most people know this type of vector notation. I tried to put all of the ugly equations on like singles, really dense slides, you know, so that people would just say, oh, this is a horror story, and let's go to the next slide. Actually, I had a reason for doing that, because a lot of times when I brief these things, I don't really want to put all of the equations, but then my boss was saying, no, it's not clear. You get to the next slide and you have a symbol and you haven't defined it. So I said, okay, well, I'll make a slide just defining stuff. But it ends up telling the whole stored in a slide. So it's this has to do with what we really do when we process that radar data. So we measure the radar data, and it really is a representation of what you sent, the ratio between what I sent and what came back. That's the radar data. Now the question is, how do I process this to find out what I'm going to find out in our terms about the world? There's a typical way you do this. What I do is I have a model of what the phase is going to be. Okay? How do I get this model? Well, if I assumed I had a particle moving on a straight line, right, then I would know what the phase would be, because the phase is just the distance to that particle as it moves along in time, right? This is a geometrical model of whatever I think I'm seeing out there. And I can encapsulate that in a phase model, right? And what I really want to do is cancel it, right? So I take my model of what I think the phase would be if the world were a certain way, take the negative of that and multiply it by the data I actually measured, add them all up, take the absolute square. The idea is if the phasors were all lining up, it means, oh, my model was pretty good, right? In all probability, that was there. And in that way, I end up getting a real thing, which we can call the image. We sometimes call this radar cross-section. But if my phase model has a lot of different variables in it, right, different parameters going on, then this thing, obviously there's some contracting out, right? Since I summed up over the whole, all of the elements of this data cube, and then I absolute square it. So there's some contraction. So on the left, all that's left is a certain function of the parameters that I put in, which I call the generalized coordinates. So I end up with this image. I'm not going to talk too much here about probability. Maybe in the paper I will. But this thing qualifies as a probability if I normalize it. Okay, and in fact, it's a, yeah, this is a certain probability. Or it's just the energy, right? I'll give some simple examples. I introduced something called the steering vector, and this is just notational. This is the thing right here, right? It says this is the data that I measured. This is my model. And this is a result, which you could say is a picture. A picture in the world of the parameters of my model.
You want this?
No, it's okay. Nobody's confused at what I'm saying.
I think I'm following where you're waving your hand to.
Yeah, I'm walking.
And I guess if I don't, then I'm lost anyway. So.
Yeah, I'm trying to walk through them sort of linearly. In essence, the thing to view at the top level is I took a model. That's a picture of what I thought was out there in mechanical terms. I took the data, which is something operational that the instrument actually measured. And then I do a definite algebraic operation on the two, which is sensible. I'm going to take the phase of the model, negative, times the data. I'm trying to cancel it out and get coherent position. And the result of that is I'm going to get an image, and the image is kind of a density in the space of all the parameters that went into that model. Now this is already abstractification from the point of view of the radar engineers, because usually for this phase model, they assume I have one particle moving at constant velocity throughout the whole time. And that's, I would say, almost universal in radar signal processing, is to go no further. All right. And then I just did a little bit of fancy stuff here. Okay, I have the absolute square of something. I can express these things. This is the data again. This is the same expression as here. but I wrote it in a pretty way. So it's a, this is the complex conjugate of something times itself. In when you're doing complex linear algebra, if you do the, you switch the thing, you change, you get the conjugate. So that's a prettier version of what I had there, same thing. And we like it that way because it'll help. Okay, and as I was saying, there's a usually what people do is they think, I have an array that's getting the angle. I have lots of pulses coming back. That's getting the velocity. And the wideband content of the thing, that's getting the range. So they typically consider this to be 3 independent Fourier transforms that give me the 3 things. Range, from the frequency, velocity coming from that time index, it's Doppler shaped, and then angle, which might be 1 or 2 angles depending on your arrays. I'm really kind of breaking this whole thing up and saying, look, whatever you measured, I'm going to make a big vector out of it, right? My model is telling me, okay, well, let me do these couple of cases which are really regular canonical cases. If I have just an array here, then I can write down the phase model. It only depends on element, and it depends on one parameter of the world, which is the angle I think that plane wave is coming in. So you see the 2 things happening. This is that discrete index that counts over my measurement. This one here is my model parameter of the work. And I can write this phase function exactly. I'm just doing a little bit of geometry here. I just write it down. And then the steering vector is, each element of it is e to the minus that phase. So you're trying to cancel one by one the measure of the phase and the measurements. I get the image here, and the image looks like this. What this image is telling me is that I apparently saw 3 targets, and they were at specific angles from the radar. This is a good model to keep in your mind, right? As sort of the set, the category of sets, or whatever it is to say, I steered in a certain way, right? Which is to say, I assumed there was something coming in from a certain angle. Right? I pointed my flashlight over that, and I asked the question, well, was there or wasn't there anything like that out there? And it gives me this map, so that's the image. If you go to the right here, this is probably the ultimate of what most radar people do, right? I guess I get the big bucks because I do more than this, kind of thing.
You're right, I'm getting queasy.
But this is a linear model, right? If I just say I had one particle moving in a straight line throughout the entire time that I looked at it, that's going to be the linear model. If I have that case, I can generate something like this. This is a map of the ground, right? This map is just like this image, only this is a 2-dimensional image. Now I made an assumption that I had scatters stationary in a plane on the ground. So I could write down the phase function and do the same, turn the same crank. And this image is like this image. Right? In a sense, it could be telling us, well, what's the likelihood, or how big was the whatever I saw right at that point in the ground. So that's called a SAR map.
Can I interrupt? There are actually radar shadows that I'm seeing there on the
You see a lot of artifacts in this, because this isn't really a photograph, right? But there's all sorts of artifacts that people see in these.
Yeah, but I see a reflection of the ground, and I see also the ground being shadowed by the trees and the edges.
You definitely see those.
So that's a radar shadow that I'm seeing.
It's absolutely.
Well, the transmitter and receiver are not joint, they're separated in this case.
No, it's one, well, it's one transmit receive.
Sorry?
It's one transmit receive element, but it's moving. So the effect of that is it forms like an aperture.
Oh,
This way.
that's quite a long
So if your radar was stationary, you couldn't do this. Is this what you're saying?
Yeah, that's right. If the radar were stationary, you'd be limited to just seeing range profiles.
Okay, so you're taking that movement and then...
The movement of the radar is allowing me to get Doppler. That's really a range Doppler image, but it's...
I'm impressed.
Yeah, it gives you like a picture of the ground. So, and these are just kind of typical things that are done. Now this is the one where I think I accidentally, it says something about blowing somebody. There's a man in an army. But this gives you just an idea, just going a little bit further, right? In this case, I want to...
It's the schools and hospitals that look like...
The schools and hospitals look like... And by the way, right, we're very concerned with not blowing up a school or a hospital, right? So we almost want to identify those, you know, even better than we do the enemy. But this just shows a person walking around on the ground, a tree, and a rock, piece of terrain. Now the way they move, each one is distinctive in the following simple sense, right? This one here is actually some data of a human being moving. And what you see there is his arms, and the main part of his body moving. Right? But what you see in the radar phase is the equivalent of a scatterer that moves back and forth sinusoidally, and it translates. Okay? The tree, which gives problems for ordinary signal processing based on Doppler, just sways back and forth. But it doesn't translate. Okay? And the rock does neither one. Right? So, by extending this phase model from being the usual, right, R plus VT, to a phase model that corresponds to a scatterer that's doing both this and this, right? It's got more parameters. Then I end up with a space. I call this path space because each point in this space is one of the possible paths that you've modeled. Right? Each point in this space. And what you're going to see is that, you know, common sense would tell you that the trees are here, right? The rocks are down in the corner here. And the people are over here because they both sway back and forth and they translate. Right? So what it tends to do is it opens you up into a bigger space where things of different characters live in different places.
Are you telling me that I should patent radar absorbing clothing?
I'm sure you could get a patent. Now I'm going to link to bigger numbers. Okay, this is a case where I have an object in space. The object is undergoing technically a pretty complicated motion, right? An object that's rolls mass symmetric will kind of cone like this, but it's got a lot of degrees of freedom already. It's got the direction about which it comes. It's got the rate at which it spins. It's got the rate at which it does this coning thing. If you add them all up, there's 6 or 7 parameters needed to just describe the motion. Plus, if I have a scatterer attached to that, there's 3 more coordinates that describe, well, if the thing were stood up, right, in its own frame of reference, where was that scatterer in its own frame of reference? So that's 3 more. So the phase model actually has 9 parameters in it, meaning that my path space is a 9-dimensional space. Nonetheless, I can go back and turn the crank on it, and I think this is a movie if it'll run. I'll tell you later. This is a sort of sleight of hand, but what I've done is you can really find the shape of the whole object, where the scatters were in the body frame. And I've superimposed on that what you also find out by doing this processing, which is the constants of motion. So this is sort of a plot of what you get, a 9-dimensional result. And this is just turning the same crank that I showed. Only thing that changes is the phase model. And the phase model comes from your idea of what you thought you were looking for. So there's a certain sense here that you get. That there's the data that you measured. There's the model, which is what you were thinking you saw, right? And then you get out of the whole process this density in the space of parameters, and it's kind of telling you, you know, gee, there was a particle here and it was moving like this. It looks like there were 10 particles and they were moving like this. You know, my tendency, even in my talking here, I guess, is to think that operationally these complex numbers that the radar measured are more the reality, and the other thing is something, it's mixed with a model of what we think things are like. This one is going to get too terrible, and I'm not going to go in great detail through this. However, it's kind of a beautiful thing. I can bring into this sum weights. Now, we often put in some weights into the sum, and if they're real numbers, it doesn't really change the fact that if there were a scatterer here, it's still there. It just changes the kind of a fall off and the little lobes on the side. We do this type of thing to make images look better. But if I let these weights be complex numbers, now anything could happen. It could, for example, make one region of the path space very sensitive, and it could put a big null in another region of the path space. That's chiefly what you want to try and do. So in the formalism, what I've done now is I took the data and I combined it with the model, right, which ordinarily would be kind of a bad thing to do conceptually. The reason I'm doing it is to bring the weights out to the, kind of directly to our attention. So I take this formula, which is a simple thing, weights times the data times the phase correction, absolute square, that's going to give me my image. And what I do at this point, because I've modified that cube, is I can pull those things to the outside. And in the Dirac notation, you see it takes on this form. Those W's are on the outside, and I have these Q's on the inside. The physicists will squint their eyes up and put psi in there instead of W. But what I can do, and this is just Bayesian probability, is now I can actually define the classes of objects that I'm looking for in terms of points in the path space. More explicitly, I'm going to make up class conditional densities in the path space. Just like the one where you saw the rocks are about here, the moving trees are about here, the people are about there, right? So you can see I can make a model that says, okay, here's a probability density that says, right, if it's here, it's a rock, if it's here, it's a... So I end up making, I can build up, this thing really points to one, this operator QQ is a projector that points to one place in the path space, to one path. But I can integrate, and now I'm pointing to not just one path, but sort of a blurred out region, right? But it's an operator that points to that region. And the way I do that is I'm pulling these W's outside of the whole thing. And you see what you get in there. It's a little bit complicated, but what I have is steering vector, conjugate transpose, times this probability density, times the steering vector going the other way. That's a matrix, and I integrate it, I get a certain matrix. The important thing is this is all the model, and I can just calculate this matrix. It's all model. I have the phase, go through the magic business, I put it in here, The idea is I would like to find the weights, the window, that makes guys over here light up and makes some guys over here go away. You can see why I would do that, because I'm interested in guys over here and I'm disinterested in guys over here. So I want my image to do that. And these are typical cases where you would do this. In the beamforming example, if I knew I had some interference coming from certain directions, jammers, and I wanted to get rid of those and still see the scene, what I could do is set up the exact same formalism here. My probability density, my class probability of something I want to see is kind of uniform across, or I have a guard band. My probability of the jammer are like deltas here, delta functions. And I can plug that all in the thing. And here's the beam that I formed. This is analogous to that picture where I just saw the beams, meaning there was a plane wave coming in from the wall stack. But I've used a couple of degrees of freedom and made extremely deep nulls, 100 dB nulls, where the jammers would come from. So this is the pattern. So the end result is I don't even see that bad interference, even though it's loud. And I can still make out other things that I'm interested in.
So the interference generally is kind of like the sort of gross. You can recognize it as noise or something.
It's not noise. It's actually, this kind of interference is like jamming, is extremely bright compared to what you're looking for. Another case, you're looking on the ground for moving things, but the ground is very bright. Very, very bright. So the reason...
You presume you're not usually lucky enough that your jammers are nice and pure like that, aren't they? All over the place.
No, actually they try and come in from a specific direction because they're...
Not quite, but because they are in place, but
they want to get maximum power.
When they're shifting frequency and the rest of it.
That all comes out in the wash. If you knew the spectrum...
So you're still using 100 dB spatial.
Yeah. Yeah, if you knew the spectrum of the jammer and you put that in, you could get even deeper knowledge. So these are some typical cases. But in general, I can just push this through to whatever my model was of the world, whatever parameters went into that phase. I'm trying to just draw a picture of it, and now this is really an n-dimensional space, right? The one density is where I think I'm looking for signal, and the other density is where I'm looking for stuff I don't want to see. And I can still push this same thing through. I can make operators for the signal, for the interference, and here I'm just saying maximize the ratio of these two things. You can really do this with Bayes' rule properly in probabilities, and then you can have multiple classes, as many as you want. And you can find the operator that corresponds to weights that would see one and not see the others. When you want to maximize a ratio like this, it's called a Rayleigh quotient, but this one is complex. And it's a well-known mathematical problem, and it leads to an eigenvalue equation. The astute physicist recognizes this as the Schrödinger equation. Just a couple of comments about polarization. This is where I think I sort of start to get into your area. I was reading your book a little bit last night. What I do know about polarization is that in addition to having these frequencies that really hit the thing quite independently, light has two polarizations. It could be the helicity going this way and that way. They could be vertical and horizontal, linear, right? But it consists of two components, not just one. You just know this about light, it's polarized. In that case, really what happens is a transformation that tells me, well, the left the left polarized stuff mixed, and some of it went into the right channel. Some of the right went into the left channel. Right? So instead of just getting one single amplitude, I end up getting 4 amplitudes that form a matrix like this. So the operation of scattering by the world is now not just a complex number, it's a 2x2 complex matrix. And this 2x2 complex matrix, there's a unitary operator basis for 2x2 complex matrices. They're called Pauli matrices. What that means is I can just write in a 2x2 complex matrix as a linear combination of these with complex coefficients. And I've trickyly just called these X, Y, and Z. So what it means is that the world looks to the polarized radar, if you keep track of polarization, not like the complex phase and amplitude shift. It looks like a quaternion. This is almost seldom done, but what's going to happen in my formalism is now that instead of having to fix the phase, I have to fix the quaternion. And I fix the quaternion by modeling something which is really, I guess, using group theory. It's an element of U1 cross SU2. So it rotates it does a unitary rotation in the matrix space. Plus it's still got in front of it a phase and an amplitude. So I can say my model gets promoted to this model that operates on quaternions. There's not really very much change in the formalism other than this. But you can sort of see how this gets you into quaternions, and I think, I mean, I thought a lot about how you get space out of these things, and I think at the end of the day, polarization is what gives you space, three-dimensional space.
Just complexify the parameters, you get quaternions or vice versa.
Yeah. So they have complex, these are, right, what I call a quaternion is an expansion of a matrix in Pauli matrices. But if you put an extra I in there, I think you get Hamilton's.
Yeah, you get the standard quaternions.
This is more about my multidisciplinary thing, and I think that this talks a little bit to just the situation we're in right now. I'm actually talking quite a bit to some biologists that are at the Rockefeller University. And these are the guys that show me films of DNA and RNA. And they're still thinking of them as organisms and all this. I would say at this point that this type of radar signal processing could do a great deal, but even DARPA is not interested in it anymore because they figure they're doing enough with their radars. The physicists, there's really a what now, right? Because I guess everybody sort of follows this popular. A couple of generations of theoretical physicists were raised on string theory, which was a boss. I don't mean to insult anyone in the room, but I guess it was did not prove fruitful, just a general conclusion. But she wasted 25 years of NSF funding, and probably in your country as well. So you've got a lot of physicists that just have no idea what to do. And I would say coming down the pipe are new numbers that the standard model won't match. So now it's going to be a real, which I guess it always is in a certain sense. I'm just joking about mathematicians, okay? In New York, they're all going to Google and Facebook. Everybody's suddenly interested in big data and graphs. But mathematicians are always up for any job. So, this is a quote that I like to use.
No, I don't buy that. Any job may be offered to mathematicians.
We'll go for the highest bid.
Why is Google hiring
I mean that in
mathematicians?
only Google is hiring.
Yeah, no, I mean, why is that a speculative idea?
Oh, it's not speculative, that's not speculative. But I'm starting into the speculative part here, right?
Yeah.
And what I want to do is try and tie what I've said about radar to quantum. The atom is a radar. That's a picture of the Balmer series. And if you look at that and you say, well, there are transitions that go from lower to higher, right? Absorption of a photon. And there's transitions that go from higher to lower, and that's emission.
This is sort of Heisenberg's point of view.
Yeah, it's a Heisenberg type of thing. So if I have an atom, and in particular, you know, I've sort of favored frequency over time implicitly in everything that I did, because it may be algebra simpler, but also it embodies a point of view. Now, when you get into quantum mechanics, right, energy is equal to h bar times frequency, omega. And you almost sort of, to make any sense out of it, you have to favor frequency. Because now these spacings in the frequency domain are unequal, right? You have if you're doing a Fourier transform, it's onto this really wildly wackily space, right, range. It's not like a regular discrete Fourier transform. This isn't one of these cases where you want to get out of the room, so you've actually made it.
No, it's basic, but
here's my speculation, okay? I'm not impressed with particles, fields, time, space. The ontology, as I see it, is there's an array of state transition amplitudes for the atom, and that is the base reality. The one that we're looking at is definitely calculable from that by the exact methods that I showed. Right? I dream up a phase. The phase would correspond to some things moving around in the world. I shine the flashlight and see, is it there? Right? And I see the people in this room and all that. So that our physicality is a little bit displaced from what's really happening, which is atomic state transitions. But in a very clear way, because the atom is a radar, except in one respect. Those frequency lines, the energy levels, are not at all equally spaced. That's the one difference from the way I've treated radar formally. But everything else, in terms of modeling the phase, based on an idea of how things are moving, and then just seeing if it's there. Right, so it's not exactly like a Platonism, right? It's not, okay, I have to take a look and see if the things are there. But this taking a look is a bit displaced from the actual data recognition. Now you can see that, and this is also Heisenberg, right? If you get up to high energy levels of this thing, now they become almost equally spaced, or you can kind of, right, they're tight. I can replace it with an equally spaced thing. Replace it with a continuum. And then, at that point, I recover everything that I can do with the regular radar. The particles, this is speculative. We have the electromagnetic field, right? And we're supposed to have these positrons and electrons that annihilate each other, and they kind of do all this interaction and stuff, right? I'm visualizing this only as atoms. You get the atoms into highly excited states, and the atoms start to look like they have 2-point particles in them. To us. I mean, on this side of our model. We've got, now, the reason I choose this instead of the hydrogen atom, obviously, is because the hydrogen atom has difficulty, that it eventually decays, or it loses its electron to something else, right? It all gets, so it doesn't stay, it's not an entity that has persistence forever. So the frequency analysis doesn't work out well. So you need entities that hang around forever. So what I'm postulating is that one electron and its friend, its positron, are really an atom. They're really a radar. You get them very, very excited, and they look like two things flying around and all this, right, to our classical view. But the thing itself is actually a radar. I mean, it's not in space. It's radar. So it's receiving this transfer function. The other one I put up here is a proton. Lifetime at least 10 to the 31 years or something like that. So looking like that thing never decays. And again, we know about the quarks and gluons is that if you give it a big bang, right, it looks like it's got 3 pieces flying around there, and then it settles down. But we know that's just an atom, because the quarks never come out of it. I'm proposing that the electron and positron never actually get out of this atom. That's not maybe so crazy, because we have something called renormalization, where in essence we're taking the top end, we're doing a cutoff on energy, right? And we kind of play fast and loose with where that is to make things work. So my idea is that this is a 2-like atom, this is a 3-like atom. Right? The biggest speculation is that we may not really have that. There may actually be identical things, which I know, like you object, but it would be interesting, and maybe this gets into the categorical ideas too, I don't know, right? But you could imagine that all you really need to know is the amplitudes for state transition for one single one of these and one single one of these, right? And maybe they map to each other in a certain way, because they're all connected, right? This guy has to talk to that guy and that. So that's sort of the worldview, right? Atoms are radars. They do the same tricks we do in order to make sense out of it. And fundamentally, we just got some fundamental atoms that just stay around forever. These 2-like things and these 3-like things, right? So we can get theological. Yeah. They talk to each other. It's a conversation. The world is, the conversation.
Cool. Can you comment on it? You're showing what's trending there in the most elementary sort of form, just the 2 elements flying around in a circle like that. Well, clearly, by any ordinary sense of electrodynamics, that arrangement radiates like stink, and of course the problem still exists that what we're talking about obviously isn't simply like that, otherwise
yes, that's right.
it will lose all its energy pronto.
Right.
That means there is an unknown structure in that area. We haven't got a very good basis for understanding what we're looking at, so looking at it is going to leave you with considerable problems then.
In my view though, you're mixing a little bit the expectation. Look, the reality, I'm saying, is just the state transition amplitudes at this point. Now, what you're going to see, how you're going to see these things moving, or what's their propensity for moving a certain way, if we think of them as point charges, in the high energy states of this thing. That's complicated. That could be very complicated.
Yeah, if you think in terms of just radar, then space and time coordinates arise out of echolocation. If you think in terms
They
of
do,
that.
and they also arise out of polarization.
How are you thinking of it arising out of polarization?
The way that could happen is if I have an object that actually has a polarization axis, like a spin axis of its own, and I model this as going past me, then polarization changes in a certain expected way.
Oh, I see, yes.
Okay, so I model that
Right.
change in polarization as though I had something going past me that had a spin.
So if you think of the world as consisting entirely of transitions and radiations like that, then somehow by taking up all that information about echolocation and polarization, there comes out this relatively coherent, at least on the macroscopic scale, picture of a geometrical world.
That's right.
So if you start in this pre-space-time form, then there must be some assumptions one can make about it that would tell you that it would give rise to.
Yeah, I think that the 3 + 1 dimensions of space, right, are coming out of the polarization. And that's, remember when I said when I promote the Z matrix to have quaternion values in it, now the correctors that I put in there, right, to try and now line up the quaternions and make a bang, right? Those correctors now bring in something else, their quaternion value. And when you look at geometry, you're making a model that says, you know, I have one object that has an orientation and it's right doing this. From that model, I say, well, if that were true, I would have this progression not only of phase, but of polarization. And so I model against that. So in that sense, I mean, I think there's always a suspicion that space comes out of polarization. You draw Feynman diagrams and now planar diagrams. What happens at the vertices are gamma matrices that are polarization operators.
I think that one of the hints that it's a right point of view is the fact that relativistic transformations are so much simpler in radar coordinates.
Oh, that's absolutely true. Yeah, relativity is, of course, in this right from the beginning. We don't have to put that in here, as long as you do the radar physically. So that's why I call this speculation. You know, these are speculations, but this is sort of a kind of points to a program, instructive program, right? Where certainly we have a good idea how we would model this stuff, so what our phase models would do. And then there's a lot of other quantities I haven't talked about, you know, charge, mass, clearly tied up with quaternions, but I think when I get through the rest of Peter's book, I'll know exactly how.
I'm interested in this sort of idea that angle is the information, because one of the things I've thought about is that if you do Pauli exclusion for using antisymmetric wave functions in the Nilpolten format, you end up with simply the expression for two fermions. P1 cross P2 is the only information left. Now, that's only non-zero, so that those are only different from each other if the P1, P2 are at different angles. Nothing else matters, just the angle of that one thing, which you could consider a phase. And I just think that's interesting how that works out. That's just an angle, bit of angle information is the only stuff that creates that object as a different one from anything else. That's the spin direction. And the other way you can think of that also is that because you can draw that as a line somewhere, then there's a plane perpendicular to it. It doesn't matter where along the line. It doesn't matter how big, it doesn't matter if it's infinite in size. But all those planes cross each other. By crossing each other, they construct a Euclidean space.
Yeah, I mean, presumably I have a line of sight, right, instantaneously. And I have I won't say presumably, that's the model. And this other one vector, the two vectors make space.
Yeah. Well, you can either do it as the plane or the line. But whichever you do, that is also consonant with the idea of the area being the only information that matters in the choreographic principle.
Is this of interest to you, do you know, as a conversation?
Yes.
Because that's one of the things that I'm picking up about it, that, you know, and that's, you know, yeah, going to like a shifting again.
When you get to this slide, this level, right, I think it has a lot to do with this categorical stuff. It's getting down to, you know, what the entities, what their bare metaphysical structure is. Something with 3, something with 2.
Yeah, it's a 2. There's a 2 and a 3.
A 2 and a 3.
And they're different. They're fundamentally different. There's some different symmetry involved in the 2 and the 3. And I've always believed that in the weak interaction that there isn't any true connection. It's just any sort of, doesn't matter what distance it is, there's a connection between the fermion and anti-fermion or whatever, in whatever way.
Yeah, I mean, all the things, all of the relational things, right, are yeah, they're definite functions. How far away the things are, and all this stuff.
I see the weak interaction, which is what this is, positron, as being a harmonic oscillator, creation and destruction.
Right.
Comes together or it doesn't, or it drifts apart.
It's going to get complicated, you know, when you try and have these two things occupy the same world, in a sense. Because now you have, you know, you're going to calculate from very different ontologies.
Well, that one, the proton, etc., also has the same properties as the positron and the electron for that interaction. But the positron and electron don't have the properties that the proton has.
Right.
But the proton does have it, otherwise you wouldn't. I'm just trying to think about the proton certainly has it because it behaves like a fermion.
So, I mean, I'm interested in all of these metaphysical aspects of it, but I'm also interested in really the physics because I see these numbers coming down the pipe, and I'd like to calculate them.
What sort of
Get them right.
numbers? What sort of numbers?
Oh, I mean, the same sort of numbers that were wrong in 1948 when people had to sweep stuff under the carpet. It's coming back.
This is not a pipe, is it that?
I hope this isn't sweeping under the carpet, but
This is not a pipe. It's not that.
Oh, right, it's in the
maybe. I mean, one of the things that comes out of this, I think, is that, remember when I said this is quantum mechanics only because the line spacings are not equal. What it means is that a lot of this radar stuff, I mean, whatever is supposed to be spooky about quantum mechanics was already there. And we're just talking about radar.
Do you know, I didn't actually understand that bit when you said about it. It's only quantum mechanics because the lines aren't equal. Do you?
I mean, I just
Well,
rewrote.
you can tell me about that again.
I just rewrote radar theory in Dirac notation. Okay, and it has neither more nor less spookiness at that point than it had before. And all of the stuff that people consider spooky about quantum mechanics is already present in radar. You don't have to go to the quantum regime.
Well, I think we should wrap this up.
Yeah.
So go to the next talk. Any other specific questions? Then let's thank him again.
Wrong again. We have a cup of tea break.